1895, Herbert George Wells wrote the science fiction novel The Time Machine, introducing the idea of time travel. But it was only after Einstein's special theory of relativity and general theory of relativity emerged that the practical possibility of time travel became known. Traveling into the future is not only possible but has actually been achieved. Cosmonaut Sergei Grigorievich spent 803 days in space aboard the Mir space station. According to Einstein's theory, time flows slower in a moving object compared to when it is at rest. Grigorievich moved at a speed of 17,000 miles per hour, making him 1/48th of a second younger than his colleagues on Earth. If Grigorievich had traveled to Betelgeuse, which is 520 light-years away from Earth, at 99% the speed of light, and returned to Earth in 2015. According to the cosmonaut's time, he would have aged only 10 years, while in reality, 1,000 years would have passed on Earth, making it the year 3015. This is the twin paradox, but in reality, it is not a paradox but a completely logical phenomenon in special and general relativity. This phenomenon is now used in high-tech GPS, so traveling into the future is achievable, requiring only funding, technology, and time. Traveling to the past, however, is a challenging issue. Special relativity does not allow it, but general relativity offers many solutions, some of which enable travel to the past. Does the actual universe forbid travel to the past? Travel to the past is not forbidden by general relativity. Here is a paradox of traveling to the past. Suppose a traveler goes to the past and kills his mother when she was a young girl. What does this mean? If the girl does not come into existence, she cannot be the traveler's mother. And if the traveler is not born, he cannot travel back in time to the past. This is a paradox. However, a more acceptable scenario could occur. Suppose the traveler goes to the past and saves a girl from being killed by someone. This girl grows up and becomes the traveler's mother. Now, the causal loop is logical and contains no paradox. Thus, the principle of causality imposes some restrictions on scenarios that express the paradox of traveling to the past, but it does not exclude the possibility of traveling to the past. The first person to use general relativity to describe a universe that allows travel to the past was Kurt Gödel. He is the author of the famous incompleteness theorems, which limit what can and cannot be proven in mathematics. Gödel presented this model to Einstein. Gödel's universe has two characteristics. First, this universe has rotational motion that prevents gravitational forces from contracting the universe and creates stability in an Einstein universe. Second, in Gödel's universe, a traveler can go far away and return to a point in his past. After completing an orbit around one side of a giant cylinder, physicists call such trajectories in spacetime closed time-like curves, CTCs. Closed time-like curves are trajectories that pass through spacetime and return to form a closed loop. In Gödel's rotating universe, these curves orbit the universe, similar to lines of latitude on Earth. However, there is no evidence for the existence of a rotating universe. Gödel could only prove that general relativity accepts the existence of closed time-like curves. And general relativity does not exclude travel to the past, but Gödel's model does not align with reality. According to theoretical physicist Julian Barbour, Einstein knew about the existence of closed time-like curves since 1914. For many periods, cosmologists have tried to construct closed time-like curves. Currently, physicists are actively searching for them in regions of the universe. Whereas earlier, Gödel sought them in the entire universe. In general relativity, planets, stars, galaxies, and all objects with mass curve spacetime. Conversely, curved spacetime dictates the motion of those objects. Under extreme conditions, spacetime can create trajectories from the present to the past. In 1983, theoretical physicist Kip Stephen Thorne explored the possibility of creating closed time-like curves using wormholes. This is a type of tunnel connecting two different locations in space-time, allowing travel to the past. Wormholes differ from black holes in that wormholes have an entrance and an exit, while black holes have only an entrance. Theoretical physicist Michael Caron stated that, in general relativity, if we connect two different locations in space, we also connect two different regions of time. The entrance of a wormhole could be a three-dimensional gateway, leading into a four-dimensional tunnel in space-time. Although physicists have written equations describing closed time-like curves, every proposed model still contains many problems. According to Caron, to create a wormhole, negative energy is first required. Negative energy is spontaneous energy, dropping below zero. Without negative energy, the wormhole would instantly collapse inward. However, negative energy is a contentious issue in physics, leading to anti-gravity. Anti-gravity requires negative energy to be created. Negative energy exists in some quantum mechanical systems. Physicist Paul Davies proposed a scenario where a wormhole could be created using an accelerator, then the wormhole needs to be enlarged. Use negative energy, as in the Casimir effect, to stabilize the wormhole, prevent it from becoming a black hole, and place it in the universe. A cosmic worm enters the wormhole. Mouth number 2 of the wormhole near the star neutron later creates a strong gravitational field, slowing down time. Because time at the other mouth of wormhole number 1 flows faster, the two mouths of the wormhole will be separated not only in space but also in time. Assuming the wormhole has been created using negative energy, we need to turn it into a time machine. Particles must enter the wormhole and exit, forming a closed loop multiple times. Kip Thorne said that black holes are an inevitable phenomenon in general relativity, while closed time-like curves are a difficult phenomenon to create. An astronaut entering and exiting a wormhole would travel from the present to the past. As mentioned, one mouth of the wormhole must lie close to the surface of a neutron star. The gravitational field of the neutron star will slow time at that mouth, and the time difference will accumulate between the two mouths of the wormhole. Suppose the time difference is 10 years. The first astronaut entering the wormhole in this direction would take a 10-year leap into the future. If the second astronaut goes in the opposite direction, it would be a 10-year leap back into the past. And if he returns to the original point in the past, it could happen that he returns home before he even left home to board the spaceship. It is noteworthy that closed time-like curves do not contradict general relativity. He wanted to prove that closed time-like curves are impossible, but we cannot prove that. Einstein's general relativity has created things that seemed impossible. But by studying those seemingly impossible things, physicists have taken another step in understanding the universe. According to a recent interesting idea, if the universe does not allow travel to the past, then the universe itself could not have formed. General relativity describes the universe at the macroscopic level, while quantum mechanics describes it at the microscopic level. However, quantum mechanics creates the possibility of accessing closed time-like curves, considered from the early infancy of the universe. At a small scale of 10 to the power of -30 centimeters, the topology of space-time fluctuates, and those random fluctuations can create closed time-like curves. Could we perhaps amplify those fluctuations to create a time machine? Certainly, creating closed loops in space-time at the quantum or cosmic scale would require extreme physics, and that extreme physics actually existed in the early infancy of the universe. In 1998, Richard Gott of Princeton University and Li Xinli of Peking University published a paper proposing the idea that closed time-like curves are not only possible but also necessary to explain the origin of the universe. Richard Gott stated, "We studied the question of whether the universe is its own mother, and whether closed time-like curves in the early infancy of the universe allowed the universe to create itself." The two scientists started with inflation, as in the standard model of cosmology, where all energy drove the initial expansion. Currently, many cosmologists believe that inflation gave birth to many universes beyond our own. Richard Gott thinks that once started, inflation is hard to stop, and that creates infinitely many branches. We are one branch among those, but we must ask, where is the tree trunk? Lee Zinli and Gott believe that one branch looped back and grew into the tree trunk. A simple sketch of two eras can be represented similarly to the number 6, where the spacetime loop is at the bottom, and the present universe is the branch at the top. An inflationary burst, according to the two scientists, allowed the universe to escape the time loop and expand into the present universe. It is hard to refute this model, but this model itself has not confirmed that the universe emerged from nothing. Alexander Vilenkin, Stephen Hawking, and James Hartle proposed a model of the universe emerging from nothing. According to quantum mechanics, a vacuum is not empty but full of virtual particle pairs continuously annihilating and being created. Thus, these authors believe the universe emerged from that environment, while Richard Gott believes the universe emerged from the universe itself. And Richard Feynman compared the universe to a game of chess played by God. Scientists want to understand this game but do not know its rules. We see God moving the pawn step by step forward. And I thought a pawn would always remain a pawn until it gets promoted to a queen. I thought I made a wrong move, but God said it's an extreme condition. The issue of time travel is similar to that. We must consider physics under extreme conditions. Traveling to the past is not an impossibility. Promoting a pawn to a queen is part of the general theory of relativity. Such ideas seem closer to philosophy than to physics. But quantum mechanics and the general theory of relativity allow us to think that those ideas are also very close to physics. In the future, could the theory again exclude the possibility of traveling to the past? Probably not. Moreover, the universe may be much stranger than we think. There might exist some symmetry that allows travel to the past. Time travel to the past is not forbidden by the general theory of relativity. But to undertake that journey, scientists still face many difficulties and challenges, which they are currently seeking to overcome.